In this tutorial, we'll be looking at our audio pre-processing pipeline. In the first section, we'll look at the best way to pre-process and represent our audio data for our machine learning model. And in the second section, we'll actually be looking at our keyword spotting model. So the first thing we'll do is import all our necessary libraries. So go ahead and do that. And this cell is what this cell is essentially doing is defining an audio recorder for our collab notebook. So it defines essentially your GUI. It records your audio using your microphone, pre-processes the WAV file, and then returns a NumPy array of your audio magnitudes. So that's what this whole HTML file JavaScript code snippet is doing. And we define a simple get audio Python function to read that data that's gotten from our microphone, pre-process it, and return a NumPy array. So just to give you an example of how it would look, for example, if I run this cell, right now it's recording my audio. And when I click on this button, it stops recording. And then you can play back your audio to see whether it's a satisfactory input sample. So what you could do for this tutorial is either record your own audio, or you could use some default audio samples, right? So what we're going to do is record yes and no. So our keyword spotting model is going to be able to differentiate between yes and no. So we're going to be recording a loud yes, a quiet yes, a loud no, and a quiet no. So question one, why are we recording both loud and soft versions of the word? So the answer here is that you want to create a more robust model, and you can't expect there to never be any sort of background noise when you are testing out your model. So yeah, so you could expect a user to be saying yes very quietly or really loudly, and your model should be able to pick up on both of them. So the answer is essentially to be able to generalize better to different sort of voices, different sort of versions of your word, with and without background noise, and etc. So if you are saving your own audio samples, which I recommend that you do, you can save your audio files as a pickle file. If not, you can load in some default audio samples, and again, load them as pickle files. So if you actually print this example audio sample, you see that it's just a NumPy array of magnitude values. So a pickle file is essentially like a Python version of your XML file. So it stores your information along with some of the corresponding metadata. Okay. So what we've done so far is we have either recorded our own audio samples for yes and no, or we've loaded in some pre-recorded examples. Either way, when you inspect them, you'll see that they are just NumPy arrays of magnitude values. And then you can also play some of the sample audios or replay back the audio sample that you recorded just using this audio function, which is a Python library function. Okay, so now that we have our audio samples and they're essentially NumPy arrays, we're going to be visualizing them. So here we just plot our NumPy arrays essentially. So here are our magnitudes against time, or in this case, it's just magnitude against the number of samples that we have. Okay. So the best way to extract features from audio signals is to actually convert them to a frequency domain. And we'll be using fast Fourier transform to do so. We'll be just using NumPy's inbuilt function, and we won't really be doing any of the math. So once we do that and we plot our audio signals in the frequency domain, this is the output. So we get amplitude on the y-axis and frequency on the x-axis. And yeah, so like we saw in a few tutorials back, the features that our model is able to pick up on need not make sense to us. So um, the difference between a yes loud and a yes quiet and a no loud and a no quiet might not be so obvious to us, but it would be for um, a machine learning model. Okay. So now that we have our audio samples in the frequency domain, we have to keep in mind that we don't want to lose information of time. So for example, in a speech recognition example, you would want to know if one word is said before the other or after say a particular word. So timing of words is important. So you don't want to lose out on timing information. So audio for machine learning models is actually converted to a form called spectrogram. And spectrogram has your frequency in your y-axis, and it has time on the x-axis. And the gradients actually indicate the magnitude or your amplitude. So these sort of feature maps or images are essentially frequency versus time images. And these now are just feature maps or images. And this whole problem now becomes an image classification problem. So these are your spectrograms now, and you again can use some inbuilt Python functions to create your spectrograms and plot them. Okay. So now these are your spectrograms, and these are essentially just treated as images now, and they are fed into our keyword spotting models, and then it becomes an image classification model. So an image classification model between yes and no. Okay. And finally, we'll be now converting our spectrograms to the MEL scale, uh, just to get information that's more perceivable uh, based on what humans say. So these are spectrograms, and now once we convert them to these MFCC images, feature maps, these are now in decibels. So you have your yes loud, yes quiet, no loud, and no quiet. Okay. Okay, so that's all about pre-processing our audio data. Now we'll be looking into our keyword spotting model. So we will not be designing the model. We will be loading in a pre-trained uh, audio recognition model that's actually present in the examples for TF Lite. So you can click on these links to get to know model specs a little more. So let's import all our necessary files. And even though we're using a pre-trained model, we'd want to tweak it just a bit to fit to our application. So our application has the yes and the no word, and we are trying to differentiate between the two. So what you can do here is define a string with all your words delimited by a comma. So here we have only yes and no, so it's yes, comma, no. But if you want to create another application where you have multiple words, you would list them all here within as a string and all delimited by a comma. Okay, so this is something that you could change for your application. Okay, so we have yes and no as our labels for our classification problem, but we will also include two new labels. We'll include a silence and an unknown label. This is primarily application specific, but in some critical applications, when you're not sure between yes and no, uh, and you don't want to take either, you just want to have a default setting where you probably just don't do anything. You could have an unknown or a silence label. Okay, so we include two new labels for our training. And this cell is essentially like a config file. So you define some parameters like the directories for your logs, your data set, um, your directories or your file paths for your TensorFlow models and your TF-Lite models and your quantized models. You also determine some parameters with respect to audio preprocessing, like sample rate and frequency. And finally, define some config details for your model, such as the URL for your data set that we'll be using, as well as the split for validation and testing. So we go ahead and load our pre-trained model. So we're going to be loading it from actually something that's called a checkpoint. Um, so we've discussed how saving a trained model onto disk will help us in the case where we can come a few days later. We can and then use the checkpoint file to just load and then run inference. We wouldn't have to train that model again and again. So checkpoints is similar, but we can actually save the state of a model at different epochs. So this would be useful in a scenario where you're training your model for a really long time, and you see that after a certain number of epochs, your model actually starts becoming worse. So you should have stopped at, say, a particular epoch number. So saving intermediate model states is actually useful in that scenario. Okay, so next thing we do is take this pre-trained model and we freeze the model. We link it to um, the settings that we have defined for our application, and we freeze the model. Okay, so this how this is done, it can be seen in freeze.py. So you can actually go to TensorFlow here, in the directory on the left panel, go to examples, speech commands, and you should see freeze.py. So you can go over this and see that actually we do pass arguments, or like command line arguments, similar to how we are doing in the cell. Okay. And yeah, so we take that pre-trained model and we are now defining a few additional parameters to that pre-trained model. We are linking it to the wanted words that we have defined and the parameters that we have defined. So this can be seen in models.py. So you can find models.py in the same directory, but I've linked it here so you can just directly click on this. And if you go to models.py, the file, you will be able to see the function prepare model settings. Let's see. Yeah, so it's prepare model settings. It takes in the number of labels, your sample rate, and some other parameters that you can read about in this file. And the last thing is we send pre-process equal to micro. So it's actually defined a few cells above in that cell that defined all our config parameters. And that's essentially saying that our pre-process is for the micro target, which indicates that we are designing and implementing this model to be deployed on microcontrollers. Okay, so this is models.py, and this is defining our model.settings or model settings essentially. And this function returns a dictionary containing these settings. And finally, we define our final audio processor model or audio processor object of class capital audio processor. So if we go to input data.py, you'll find the audio processor class, which handles loading, partitioning, and preparing audio training data. Okay, so we are now defining an object of this class, and it's linked again, so you'll be able to see the parameters that it accepts. It's linked to our URL, dataset URL. It's linked to the words that we define, the percentage of silent and unknown labels, our validation and testing percentage, and it's linked to these model settings that we just defined above. Okay, so that is defined by this audio processor class. Okay, so this cell would take about 15 minutes to run. Okay, so now we have our TensorFlow model. we've done all of these tweaks here and there, and we have our TensorFlow model. We're going to convert it into a TF-Lite model. So we are going to be working with two different models. We're going to be sort of comparing two different models. So the first TF-Lite model we're going to be using is just a simple TF-Lite model with no quantization. So we use converter.convert to load out, convert our saved model into a TF-Lite model. Okay. And the second model we're going to be dealing with is a TF-Lite model with integer quantization. So again, load a save model and convert it to a TF-Lite model, but we add this additional flag and define a representative data gen to bring about integer quantization. Okay. So a thing to notice here is when we create our representative data generator and when we run through, say, 100 test samples, we use this audio processor dot get data method. So audio processor is the object that we defined here. Okay. And we're going to be using the get data method. So if you scroll down in our input data.py file, you will actually find this method called get data, right? So it actually just gathers samples from the defined data set and returns these samples after applying some sort of transformation that we've defined. Okay. So the first one, for example, is how many. So here we're just returning one sample at a time with all our defined settings, and also our mode is testing. So we're going to be gathering images from our testing data set, right? So this is what audio processor.get data does. Okay, so then we've now defined both our models. So our first model is the float TF-Lite model, which is our TF-Lite model with no quantization. And our second model is the TF-Lite model, which is the TF-Lite model with quantization. Okay. And when we print the sizes, we see that the first one is around 68 kilobytes, and the second one is around 19 kilobytes. Okay. So this is after quantization. So question 2, what does audio processor dot get data do? It essentially is just gathering data or gathering data samples from either our training or our test data set and returning them back after applying some sort of transformation. And these transformations are brought about by the config parameters that we define. Okay, so now that we have our two TF-Lite models, let's do some inference, or let's do some evaluation. So to run our inference or evaluation, we need to define our interpreter, right? So we define our interpreter, we allocate tensors, we get our input and output details. And next thing we do is run through all our test samples. We set the tensor to the right index. We run inference, and then we get our output. And the next thing we do is essentially calculate our accuracy. So we get our prediction, we equate it, or we compare it with our ground truth test label and see if it's right or wrong. So this condition would return a 1 if it's true. So then you just add it to correct predictions, and it would return a 0 if it's false. So you wouldn't be able to add that to our correct predictions. Okay. So that's this essentially, this whole cell, a whole function runs your inference. Another thing here again is getting our data set. So we get our test data and our test labels again using audio processor.get data. We send a -1, and if you look at the file again, -1 indicates that you want all your data, not just one sample at a time. So we run inference on our first model and run inference on our second quantized model, right? And we see that our accuracy actually persists, even though the second quantized model is around 3 to 4x smaller than our float model. The accuracy persists. And from the input output details, you can see the index is at 0, your output details index is at 11, and The shape is defined, you have your D type, and you have some quantization parameters as well. Okay. So yeah, so here we see that our model is doing pretty well. It's getting around 90% accuracy before and after quantization. Okay. So in the next section, we'll be testing this model on some example audio. So we can load some example audio samples from this website, and we have 4 sample yeses and 4 sample no's with their corresponding sampling rates. Okay. So you can actually just listen to some of these. Um, you should be able to hear these audio samples when you play them. Okay. And we're now going to test our model on these example files. Again, import whatever necessary libraries that we need. We're going to run inference on these audio samples. It's similar to the previous cell where we define our interpreter and we set and invoke and get tensors. The only difference here is that these audio samples sometimes might have, these audio samples actually might sometimes be really long, but the word that's important, that's like yes or no, might really just be a small fraction of the audio sample. So we use this library called extract loudest section to just extract the part of the audio sample that's important to our model, so that we don't waste compute on audio that's really not required. Okay, so the only difference is that we have this extract loudest section to extract the loudest part or the most important part from our example audio samples. Okay, then you go ahead and test this model, and it should tell you whether the yes is now predicted as a yes or is predicted as a no or unknown or silence. And the last thing is you can actually test the model with your own data. So again, define this whole audio GUI or audio recorder GUI, and you can just give a sample yes or a sample no with and without background noise and check whether the model is doing well on the test sample that you've given.